In today's note, we are going to kind of look at all the applications of quadratics that we've looked at over the past unit, and we're going to apply it to different context questions or word problems. So we're going to be using a variety of different methods and applying some different concepts, but it all relates back to quadratics. So in the first example, the path of a ball thrown from a ledge can be modeled by the relation h equals negative 4.9 t squared plus 19.6 t plus 11, where h is the ball's height in meters and t is the time in seconds. So just some things to kind of remember. I'm going to go through and highlight. H is the height, t is the time, and we have our equation here that relates the two together. Looking at this, I should recognize that it is a quadratic in standard form, which we know, or we should know already, that does tell us some key information. But what I'm going to do first is I want to complete the table and then graph the relation. So basically, anytime I'm asked to complete a table and I'm given an equation, I need to sub in values for t and solve for h. That's essentially what it's asking me to do. In other cases, it may be sub in values for x and solve for y. In this case, it's t and h because that's what we're given. So, just as an example, for the first one, when t equals 0, we have h equals negative 4.9 times 0 squared plus 19.6 times 0 plus 11, and we get h equal to, h equal to 11. If we want to do the next one, t equals 0.5, get h equals negative 4.9 times 0.5 squared plus 19.6 times 0.5 plus 11. And we repeat this pattern. And let's see what we get for h. So negative 4.9 times 0.5 squared plus 19.6 times 0.5 plus 11. We get 19.6 roughly. If we do the same thing again, and we just plug in 1, 19.6 times 1, you get 25.7. And again, you go through the same process. You plug in next one, 1.5. Get 29.3. Plug in 2. .6. And again, you keep on repeating the process. So I'm just going to use a little bit of technology, and we're going to skip ahead with a fully completed table. So our table is now complete. Now our next step is to graph this. So there are no scales here, but I'm going to assume that each scale or each tick on the side is 2. I'm just only going to put in kind of the main ones, or at least 10, 20, 30, and 40. And then along the bottom, just because we're going up by half a second, I'm going to say that each one is a quarter of a second. So each large tick is 1 second. Now what I'm going to do is go through and just kind of graph my points. So 0 and 11 is 1 point, 0.5 and 19 is another, 1 and 25, 1.5 and 29, 2 and slightly above 30, 2.5, and now we start to come down. So we do see that repetition in numbers again. which is nice because then again that means we have kind of come up with something similar because we do, or something roughly correct because we do have this kind of parabolic shape. 4 and then 4.5, it ends at 0. So I can sketch my graph here like that. And there I have my quadratic that represents the ball being thrown. So I want to model the ball's path with a relation in the form y equals a x minus h squared plus k. So I need to basically what I want to do is come up with an equation for this parabola in vertex form. And with vertex form, the first thing I need is my vertex. Luckily, because I've already graphed it, I can see where my vertex is. So my vertex in this case is 2, and we'll say 30. We'll just make it nice and even. So with my vertex being 2 and 30, I know that my h value equals 2 and my k value equals 30. Again, just from remembering what vertex form tells us. The only other thing now that I need is my a value, which I don't have. But luckily, I have many points that I can choose from that I can plug into the equation to help me solve for a. So what I'm going to do is plug in, or pick a point to plug in. And in this case, I'm going to use the point 0 and 11, just because it's nice numbers. Zero's in there, so that's going to help me get rid of some of the numbers, hopefully. And again, remember, 0 and 11 represent x and y. So in this case, I have an hk, x, and y, so I can plug that all into my general form, y equals a, x minus h squared plus k, and solve for a. So y is 11, a is unknown, x is 0, minus h, which is 2, squared plus 30. I'm going to simplify inside the brackets. So negative 2 squared plus 30. I'm going to move the 30 over and get 11 minus 30 equals a. I'm going to simplify this, negative 2 squared, which is 4. I get negative 19 equals 4a. And then the last thing I need to do is get a by itself. So I'm going to divide both sides by 4. And I'm left with a equals negative 19 over 4, which roughly rounds to negative 4.75. Now that I have that a value, I can plug in my equation, or I can plug that into my equation. Y equals negative 4.75 times x minus 2 squared plus 30. And there is my vertex form equation for this quadratic. C says estimate 2 times when the ball is 28 meters above the ground. So if I want to estimate 2 times when the ball is 28 meters above the ground, what I need to do is use my graph and go to 28 as a height. And I'm just going to draw a line across and see where does that hit my line. Well, it hits my line there and there. And if I want to roughly estimate that time, I'm going to draw a line down to see where it touches the x-axis. And those are going to be my 2 estimations. So roughly the 2 times that the ball is 28 meters above the ground, again, once on the way up, once on the way down, say roughly 1.25 seconds. And again, roughly the next one, 2.75 seconds. So just estimating. So again, there's not a correct exact answer, but you should be roughly in that ballpark. How high will the ball be at 3 seconds? So again, this is just kind of recognizing or identifying points. Luckily, we've already graphed this point and figured it out. So if I go over to 3 and then up until I hit my line, I do see that point there, which is 3 And if I go over to my table of values, 25.7. So that right there tells us the last one, so 25.7 meters, or approximately 26 meters. Again, depending on what you rounded it to. So that's one example of using an equation to fill a table of values and then plot it. Use the key points to help you determine the equation in vertex form, and then kind of estimate based on that. Moving to the next example, based on the vomit comet. So this is the nickname for a jet that's used to simulate zero gravity, or zero G for astronauts. To simulate zero G, the jet flies in a parabolic arc starting at an altitude of 7,300 meters. After climbing for about 30 seconds, the jet reaches its maximum altitude at about 9,800 meters, where the weightless effect occurs. The jet descends back to an altitude of 7,300 meters after about 60 seconds and then repeats the process. Write an equation or quadratic equation to model the path of the jet. So what we want to do here is look at kind of our key things, the key characteristics of our graph, and figure out what equation would probably be best. Because it gives us the highest point, which we should recognize as our vertex, it would be beneficial to stick with vertex form. Y equals a x minus h squared plus k. I don't know when it's going to cross or have a height of 0, so I don't know the x-intercepts. Standard form is very difficult to get from a graph alone, so in this case I'm going to stick with vertex form. So because I know my vertex is 39,800, I know my h and my k, and the only thing now that I'm missing is my a value. Similar to the last example, if I want to find that a value, what I need to do is find a key point, or any point on this quadratic. And luckily I have two of them. I'm going to stick with the one that's 0, 7,300, because with the 0 that makes it's going to be a little bit easier. There's going to be less numbers there, or it's going to make some of my numbers smaller. Again, remember that point is an x and a y value, which I can take and plug all these in to the equation and solve for a. So y is going to be 7,300, a is unknown, x is 0 minus h, which is 30, squared plus k, which is 9,800. Now I'm going to work through the same steps and work on solving for a. 7,300 stays on the one side, simplify the brackets, negative 30 squared plus 9,800. I'm going to move the 9,800 over so it becomes minus 9,800. A times, I'm going to simplify this exponent, it becomes 900. I get negative 1,500 equals 900a. To get a by itself, I'm going to divide both sides by 900. And I get roughly 1.6, negative 1.6 equals a. Now that I have that a value, I can plug that back into my original equation along with my h and k. So negative 1.6 times x minus 30 squared plus 9,800. One little thing to check, just to make sure we're kind of on the right path. If we're not sure if our a value is correct, maybe we think we did the calculations wrong, just take a quick look at it. In this case, it is negative, which is correct because we do need to have our quadratic or parabola opening down. So again, that's a quick way to check, did I get something in the right vicinity. The actual specific value, in this case, it's a little too hard to tell just because our values are so large, but at least we know we're on the right track with it being negative. So we came up with our equation. B now asks, the effects of simulated zero-G start being felt at about 20 seconds. What is the jet's altitude at that time? So basically what this question is telling me, we want to know what is the jet's altitude, or what is the H. So H equals, not zero, sorry, H equals question mark. And we're also given the time, 20 seconds. So we're being told that T equals 20. Or in our scenario, X equals 20. Because again, the equations that we've used are X and Y. So altitude, we're looking for Y equals unknown, and we're told that X equals 20. So if we know one part of a point, or one value, to find the other value, we just have to sub in X equals 20 into my equation and solve. So instead of X, we're going to put 20 minus 30 squared plus 9,800. Everything is on one side, so this just becomes simplifying and calculating. Negative 10 squared. And in the end, once we go through and calculate all this, we should get 9,640 meters as our final answer. So you could write a therefore statement if you wanted to. Therefore, the jet's altitude is 9,640 meters when zero-G effects start being felt. So again, just another scenario. Here we didn't have to create our table of values, but we did have some key points that we could use to come up with our equation. And then we use that equation now to find a value at a specific point. The next example is a professional skateboarder, Danny Way, jumped over the Great Wall of China. His path can be modeled by the relation h equals negative 0.05 d squared plus 1.15 d, where h is his height above the Great Wall and d is his horizontal distance from the takeoff ramp, both in meters. So the first question is asking us to make a sketch showing the vertex and the intercepts. So this one's going to be a little bit different. We haven't covered too much on something like this, but we're going to start off with our equation. So h equals negative 0.05 d squared plus 1.15 d. And what I'm going to do first is I'm going to common factor. So if I want to common factor, I'm going to find something that's common between both of them. Right? And I can see that I have a d value that's common, so I'm going to factor out a d. And then the second part, I see this negative 0.05 in front of the d squared, so I'm also going to factor that out as well. So if I factor that out, I need to see, okay, what's left over. So if I divide everything that I just had by that value, I'm left with d minus 23. Now that I've factored it, I need to understand what I'm looking at. So right now I'm looking at kind of a modified factored form. Right? I have my a value out front here. I have my x minus r, and I have my x minus s. Because I don't see anything in brackets with this second d, I can assume that one equation, or one x-intercept, is 0. So I'm going to have one x-intercept that's 0, and if I look at the second one, d minus 23, that x-intercept is opposite of what we see, or in this case 23. So now I know my two x-intercepts. In order to find the vertex, I need to find the middle value of these 2 points. So in order to do that, I need to add them together. So 0 plus 23 divided by 2 equals 11.5. So I know the x value of my vertex is 11.5, which is around here. What I need to do next is figure out what is the y value. And in order to do that, I need to take that x value and plug it back into the equation for x, or in this case d. So negative 0.05 times 11.5 squared plus 1.15 times 11.5. So here I've plugged it back into the original equation. You could have done it into either one. It didn't really matter. So we get y equals, and if we do this entire calculation, we should get 6.6125. So that means my vertex is 11.5 and 6.6125. So we can graph that because we can find 11.5 roughly, go up to 6.5. There's my vertex. We have our two x-intercepts. That's really all the points we have right now. So we're just going to roughly connect them as best we can. And there is our sketch of the skateboarder going over the Great Wall. B is asking, how far did he travel in the air? Well, if the height is shown on the y-axis, if he starts at 0, when he lands, he's going to end at 0. So in this case, we just have to see what is that total distance. And in this case, we see that total distance traveled goes from 0 to 23. So he traveled 23 meters. Second part, what was his maximum height above the Great Wall? Again, the maximum height, if we're not sure what point to look at, we can just look at our graph and try to find that highest point. And in this case, the highest point was our vertex. Because we're looking for the height, we're looking for the h value, or the y in this case. So the y value of this vertex is the 6.6125. So therefore, his maximum height was 6.6125 meters. So in this example, we were given standard form. We had to do a little bit of factoring to get to factored form. From there, we were able to find our two x-intercepts, and using those, we were able to find our vertex. From there, we could answer a few questions based on the x-intercepts and the vertex. Again, this is all stuff that we've covered in the past, so you may have to go back and review some of the lessons, but we have talked about using the x-intercepts or determining them, and then using them to find the vertex. In the last example, a baseball is hit in the air. Its path can be modeled by the relation h equals negative d minus 5 squared plus 26, where h is the height of the ball and d is the horizontal distance, both in meters. A is asking, what is the vertex of the relation? So in this case, our vertex, because we're given vertex form, we may have to, if you want to write that down, just to remember, so vertex form, remember our vertex is h and k. So the h and k value in our equation is the one that's in the bracket and the one that's outside. Remember, when it's inside the bracket, we take the opposite of what we see. So in this case, opposite of negative 5 is positive 5, and then this k value we just take as is, or 26. So that means that the vertex of this is 5 and 26. What is the maximum height of the ball? In other words, this is asking for our optimal value. And again, our optimal value, remember, is the y value of our vertex. Or if you think about the vertex being the highest or lowest point, in this case, because that a value is negative, back up here, that means it's opening down, so this vertex is our highest point. So what's the height? Well, in this case, it's 26. How far horizontally will the ball be when it reaches its maximum height? This is another, basically it's asking for the x value of the vertex. So in this case, it'd be 5 meters. So the ball will be 5 meters away horizontally when it reaches its maximum height. D wants me to write the relation in standard form. So in order to go from vertex form to standard form, I need to expand. So this is where we use the FOIL or the box method. Again, whichever one you prefer. I'm going to use the box method just because I feel some people people like that one a little bit more. So if I have negative, or h equals negative d minus 5 squared plus 26, I want to rewrite this so I have my two brackets. In this case, h equals negative. This square just means the bracket occurs twice. And now I can work on using the box method. So I'm going to use the box method to multiply these two brackets. I have d minus 5, d minus 5. Let me just move this down a bit. D times d is d squared. D times negative 5 is negative 5d. Same thing in this one. And then negative 5 times negative 5 is 25. Remember, when we do this, we have to add our two middle terms. But now I can put this back into my equation because I'm not quite done yet because there's a few extra things I have to do. So it's going to be h equals negative, because the negative or the negative 1 is being multiplied by whatever this answer is. So negative 1 times d squared minus 10d. So I just combine the two that I've circled, plus 25. And then at the end, I have the plus 26. I can now multiply that negative 1 through, which is just going to change the sign of everything. So negative d squared plus 10d minus 25. And then plus 26 just carries down at the end. And then the last final thing, I can combine the two last terms because they are like terms, and I get h equals negative d squared plus 10d plus 1. And this is my equation in standard form. E is asking us to make a sketch showing the vertex and the y-intercept. So in this case, we know the vertex is at 5 and 26. So let's put a point, just say out there. Horizontal distance of 5, vertical distance of 26. The y-intercept, I don't know where the y-intercept yet, but if we remember our standard form, that last value tells us our y-intercept. Another thing we could do, we could plug in 0 for d, because we know our x-intercept has to be along, or our y-intercept has to be when x is 0. So we can plug in 0 for d and solve. Either way we do it, we'll still get the same value of 1. So based on what I have my 2 points, and I'm going to roughly sketch it. And so again, that's about as far or as much as I can do based on what I know. So I have my vertex 5 and 26. I have my y-intercept of 0 and 1. And that's all I know based on my two equations. What is the meaning of the y-intercept? It should be F. So the meaning of our y-intercept, again, if we look at it, when the horizontal distance is 0, the height is 1. So the horizontal distance of 0 means when we're hitting the ball. So this means, therefore, the ball is hit 1 meter in the air. So a bunch of different examples of using all of our concepts of quadratics that we've looked at, applying them to word problems, coming up with equations, identifying key points on graphs. But again, all concepts that we've looked at in the past, now we're just kind of putting it all together in a kind of summary and application sense.